Hi, I'm Professor Goins. In this video, I'm going to show you DeMorgans Laws in the general case where the index is arbitrary, okay? So proving these is a standard technique as far as showing set containment. So in order to show that two sets are equal, we show that one is a subset of the other, and this is a subset of the first one. Same thing for two. But again, the general idea for DeMorgans Law is it shows you how to take the complement of an intersection or how to take a complement of a union. And so let's show you how to, again, write the proof of this. So what I'm going to do is I'm going to start by showing that this set is a subset of this one. And in order to do that, I have to take an arbitrary element of this collection. So X is an arbitrary element in the complement of the intersection. Okay, so it's an arbitrary element in that complement. So if X is an element of this, then what that means is X is, of course, not an element of the intersection. But if X is not an element of that intersection, then it means that it has to be not an element of at least one of those, right? If it was in the intersection, then it would be in every single one of these. In order to not be an element of the intersection, there has to be one of these that it's not an element of. So this says that there exists some beta in I. There's some index value where X is not an element of A beta. But if it's not an element of A beta, then that means that it is an element of the complement. So that says that X is an element of the complement of A beta. Well, A beta complement, of course, is contained in the union of all the complements. So this is contained in the union of A alpha complement, where alpha ranges over the entire index set. So therefore, X is an element of this union, and since X was an arbitrary element of the complement, that must mean everything that's in this complement is contained in the union, and therefore, I know that the intersection of A alpha, where alpha ranges over the entire index set, take that complement that's contained in the union of the complements. Now in the other direction, let's take an arbitrary element of this set. So now, just to distinguish between the first half of the argument, let's say let Y be an element of the union of A alpha complement, ranging over the entire index set. Well, if Y is an element of this union, then there must be at least one of these that contains Y. So that says that there exists a, let's use gamma this time, a gamma in I such that Y is an element of A gamma complement, which means Y is not an element of A gamma. If Y is not an element of A gamma, then it's not an element of the intersection of all of them, because in particular, it's not an element of this one, so therefore it can't be an element of all of them. So that says that Y is not an element of the intersection of all of these sets. But if Y is not an element of the intersection, that means that Y is an element of the complement. And hence, we know that the union of A alpha complement, where alpha ranges over all the index values, is now a subset of the intersection of the all the sets A complement of that. And since I've got both of these containments, therefore they are equal. Similar argument for the other direction for part 2 here. So for part 2, maybe pause the video and see if you can reproduce the proof for part 2 following along that same format. And then we'll start it up again and I will show you how to do it. All right, welcome back. So what I'm going to do is I'm going to say let X be an element of the complement of the union okay. So if X is an element of the complement of this union, that says that X is not an element of the union, which says X is not an element of any of these. If X is not in the union, then it's not in any of these. So that means X is not an element of A alpha for every alpha in I. But if it's not an element of A alpha for every alpha in I, that means then X is an element of the complement for every alpha in I. If it's in every single one of these complements, that says that X is an element of the intersection of A alpha complement, where alpha ranges over the entire index set. But that's the right-hand side. So hence, everything in this set is also in this set. So that tells me that the complement of the union is contained in the intersection of the complements. Okay? And then for the last argument, I'm going to take an arbitrary element in this set and show that it must also be contained in this set. Therefore, this would be a subset of this one, and hence they would have equality. So let Y be an element of the intersection of A alpha complement, where alpha ranges over I, which means that Y is an element of A alpha complement for every index value. If Y is in the complement of A alpha for every single index value, that says that Y is not an element of A alpha for every alpha in I. So if Y is not in any of these, then it's not an element of the union. But not an element of this means it is an element of the complement. So therefore Y is an element of therefore, the set that I started with, which was the intersection, must also be contained in the complement of the union, which says that everything in the complement, or in the intersection of the complements, is a subset of the complement of the union, and hence they're equal because they're subsets